G'day guys, part 2 of the VCO fix on this SD 2000, and as you can see I have added one capacitor there. That is a solid aluminium capacitor. Um, that's what Philips used to use in all their 2.0 radios, and it would lock down anything to ground. Any spurious would just get straight bypassed to ground for those. They have an extremely low impedance, and you don't want to hook them up backwards or anything. They go off like firecrackers. So that's across the supply rails on the board. And the other thing I did, I added a ground plane. Probably the most important thing to do. You can see that I have put a copper ground plane onto the board because it didn't have one, and you can see where I've just looped a bit of wire around here, soldered it on, and that's ground. These things are positive to ground. The detector's positive to ground, but it then steps up a rail. So this thing, technically, if you look at it, it's running negative. It's it's basically running negative voltage. It's quite interesting, but it's like a pommy car. So that is the VCO, but the biggest we have to redo something and stabilize that back in the device. But what we'll do, we'll have a look at the oscilloscope there. I'll pop that down because it's in the way a bit. I had to, I've got the brightness a little bit high on this. But what we'll do, we'll turn the detector on, and I've got it on a mono coil at the moment, so I'll just turn that down. But if you can see the VCO, if I adjust it now, there's no jitter. Maybe you can see jitter on the screen, but yeah, it's absolutely clean right across the spectrum there. So yeah, that as you can see, we're down at, I'll just leave it there. That's it ended up on 3.6 microseconds per division. So as you can see, maybe you can see the refresh scan rate of the oscilloscope and the camera beating together. It might be doing that, I don't know. But where that transition from the top to the bottom is, that has to be stable, and that's not moving. I mean, I could zoom right into nanoseconds, but it is not moving. It's stable. So all it took was to get rid of a lot of the noise, was to put a ground plane on it, and a very low impedance capacitor across the supply rails, very close to the active device on that board. So that is a very, very quick and easy repair. We'll call that a repair, shall we? I don't know if we call that a repair. Yeah. Or do we call that another modification? I don't know. Yeah, you can look at it either way. So, Victor, 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 low frequency is something. So, yeah, your detector is fixed, and it's working really well. It is very, very good indeed. So you can utilize the VCO part of it now, so that's all fixed up, and you've also got crystal lock as well on position number 1. It's low frequency position, controlled by a crystal. But the way this is behaving at the moment, you can see a little bit of fluff on the waveform. That's 50 hertz, just getting in and wanting to ride on everything. You can't do anything about it. But yeah, so as a matter of thing, let's go down and we'll tune this thing as low down as we can get it. Is that Yep, that's the lowest VCO frequency. We'll see what happens. I do have it on a mono. Yep, that's as low as she goes. And where are we? Just checking everything. Medium gain. Yeah, don't worry about the ground balance. I was going to check it. I've actually, if you want to have a look, I'll show you what I've got it running on. It's quite amazing, actually. You got to remember this is set up for deep gold. Well, it'll do anything you want, but anyway, we'll get around there. We go. That's my pickup coil, the little loop of wire there. But if you look up here, if I lock that and I bend this, oh, look at that. I've got it running on the tiny little mono coil up there. So there's a tiny little mono coil. And at these very low frequencies, I don't know what it'll, it's like, it's on my tiny mono coil, even though I've got this set up so it's basically ignoring a lot of electrical interference. We'll try a 0.1 on it. So even in low, with the system nicely cleaned up, so on something big, like a ring, yep, right in the air, but we got a lot of interference. Anyway, that just goes to show, listen to it. See, that's running on the VCO. It might be moving like a poof-teenth in frequency or in time. Oh, I better drop this back down because it makes no sense. Down you go. There we go. Don't want to zoom in that much. But to give you an idea with a VCO, I'll just wave my hand near it and watch what happens. Can you tell the detector speeds up? The interference, 50 hertz. I'll blow on it. I'm trying to find somewhere where it's between the harmonics of the 50 hertz power we have, and well, basically VCO is, I just touch it then. You're probably better off seeing it on the oscilloscope. That hang on, I'm going to move around here and I'll leave that there. Okay, I'll put it between the markers again. Okay, I'm just going to redo this, but I've got to have it so you can see the oscilloscope, and I'm going to have the board open. So if you have a look at this, okay, you can see that there. It's relatively stable, but I put my hand near the VCO. Watch what happens. I just put my hand near it, not on it. There you go. So that's what would have been probably happening as it's flopping around inside the detector as well. So that's low frequency. So at high frequency, that would be far more pronounced. So yeah, that's just put my hand near the wires. So it technically should have gone in a little metal box, shouldn't it, or something? But that's how it is. Without the ground plane there, I did that. It was making a massive excursion in frequency. So that is far more stable. Yeah, far more stable. And turn him off. but that's going to work quite well. So yeah, and I also redid the front end input stage on this as well. I don't know who did it, but put it this way, there was I don't like saying this sort of stuff because the person, whoever did it, is going to get their nose out of joint. That's what happens. They fire up over it and carry on like pork chops and try and defend themselves. But the device that was in there, uh, I had a look at the gate capacitance in the data sheet, and I couldn't get it out of the circuit quick enough. um, I noticed that at one stage it had the 4093 replaced. I wonder why. Uh, maybe it just the 4093 blew up because it couldn't transition that amount of gate capacitance at the low level the 4093 is capable of putting out. But I just had a look at the specs on everything, and you know, people look at one specification and don't take into account the other specifications. So now this detector has a device in there with it. Instead of, well, God, I remember looking at it and it was like, it was 200 and input capacity was 234 picofarads or something. And I went, what in hell? Now it's got a device in there that has about 30 picofarads. So the transition is a lot cleaner, and it doesn't load up the poor old 4093s these days. The modern ones only can't just, they don't dump out any current. Lucky to get a clean half a milliamp out of them. It's they're just yeah, unless you get a buffered version, and that's not a buffered version in there. So they're not good. They're good for about half a milliamp or something. And you don't want to clock them too fast. They just don't transition. They just haven't got the internal fortitude, as in the drive capability. And you stick them onto a device like a MOSFET with large gate capacitance, and it has a hard time switching it up and down, and even keeping it stable. So it's another noise source. So you got to match all the criteria of the input stage. So on this one, on the input stage there, I have put the good, fast, reliable, low noise 2SK 1334, and that is extremely suited for the purpose in the front end of metal detectors. So got to be careful. Keep an eye on if you're doing any modifications to your detector. Just keep an eye on the gate. Well, I could go into a lot of things too. What you want to look at the gate channel length as well. The longer the gate length, the quieter the device. It causes or actually helps with electron um, alignment. Basically, it stops um, low frequency noise. If you go to short gate lengths, it causes problems. Well, won't call them problems. It causes issues in low noise devices. Um, just the way it disrupts the orderly flow of electrons. Basically, it causes things to go off in a different tangent and cause noise. But we're getting down to the atomic level now, so you want relatively long gate channels. You want probably a little bit more in the way of gate distance, even though we're talking, um, you know, micro measurements here. And you want to strive for fairly low on resistance, but then you've got to look at output capacitance and basically every terminal capacitance to each other. Anything such as small signals can actually go down the couple in capacitively into the gate channel and disappear down to the drive circuit. So you, and if it's connected directly to ground, that will possibly impact what you really want to do. Now I'm going to give away all my trade secrets if I keep telling everyone what to do, and other people will do it and claim it. They do. They claim it. So that is this detector, Victor. Your detector is now does not have the brown note on low frequencies or anything on the VCO range, by the way. So yeah, I'm going to have to anchor that down. I think what the best thing to do with that, instead of just letting it float around in this part of the circuit where all the clocking circuitry is, I think what we do, we stick it on the audio board up here, because the audio board has a ground plane here as well. So it'll be double planed, sort of. Not really, but it's a far quieter part of the circuit to put something like that, where you don't want close proximity coupling through other components into the leads and so forth. You know, I could go and rewire it all with shielded cable and that, but it doesn't need it. It's stable, and as far as I can tell, there's no other clocking from all that 4,000 CMOS dividers and that getting in, so that's good. It will work. If you really wanted to, what you could do with that, you could wrap it up in a bit of foam, spongy foam or something like that, as long as it's dry. You don't want to put anything that's going to absorb moisture in there, because it'll stuff it up. And put some electrical tape around it, and then wrap it in some alfoil and ground it as well. You could do that, and that would make it better. But like I say, if we were talking at frequencies up at 10 or 20 megahertz, yes, that's sort of getting to the point where you really have to do stuff like that. But at the lower frequencies, you can get away with it, as long as you check and make sure there's no interaction with anything in the way it's made. So yeah, what I might do, because a lot of the components on here are just tacked on, it's got a potentiometer there, and even the capacitor I put there, and that I might put a bit of hot melt glue on the board beside the potentiometer. Anything that sits up on legs can break off with vibration. Driving down the road, bang, 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 and just sometimes it picks up a natural frequency of vibration and gets into resonance and breaks legs off things. It does happen. It's happened many a time, especially with cables and wires that are soldered to the circuit board. It just wiggles the whole thing, and eventually it just pops off. It just work hardens the copper wire, and you bend copper enough, and it goes brittle and breaks off. That's exactly what happens. So, yeah. Anyway, this is all ready to go back to the customer. And he should be happy with the way it's turned out. It is running quite well. So, but like I say, we can do a lot more. Like, you could probably even do a complete redesign, more modern than what that is, even though it's, I don't know. Do we call that modern? I don't know. Yeah, I don't really want to delve into it. And, yeah, but a better way of going is definitely using, if you have a very clean DDS oscillator, and you can implement phase lock loop controller, something with a very, very, very slow servo in the phase lock loop. You don't want something fast, you want something nice and slow. It doesn't make that much difference in these detectors if it moves slowly. It's only if it moves fast. And the one, when I first looked at it, was jittering all over the place. I mean, we're looking at it in the window of basically the window I've got there for the markers 3.6 microseconds. So we're looking at roughly probably one odd, one and a bit microseconds per division, and we're going closer to that, and that was jittering around all over the place. It was jittering within about a microsecond, up and down, or left and right. So anyway, fix that. That's all cured. Simple cures. Probably you look at it and you go, well, how am I going to cure that? Well, I used to design RF stuff, and you know what needs to be done. You just know. You just look at it straight away and you go, God, that's because of that. And yeah, and also putting a ground plane on there as well um, helps stabilize a lot of stuff too, and keep the noise out. Um, it's sort of getting to the point of being sort of critical, but then again, the whole circuit's got big long wires going to it, so that again. Oh, look, I could just nitpick this all day, but I'm not going to, because I don't know who designed it. Um, you know, the design's in the right direction, but the effective, application of it, yes, just fell a little bit short, I suppose. I don't know. What do you guys think? Um, you know, leave your comments, because, yeah, like I say, I don't know who did it. There's only a few people doing it, but I don't know who did it. I don't know. So I hazard a guess, but I'm not going to. I might crack it. And yeah, we'll have another attempt at World War III. So yeah, anyone with anything like this in their detectors, if it's noisy, uh, when you're scooting through the VCO ranges, just copy what I did. You can see where I've done it, I think. You just need to remember this. Ground is positive on this board, so the positive goes onto the positive. See that you can see the red wire there, I think. Hang on, I'll zoom in just in case any of you guys have got one of these and you want to fix it yourselves. I'll zoom it in and I'll get something pointing and I'll just poke it out where what is. I don't even know if these are all built the same or not, or what. I don't know. I just don't know. I don't see this sort of stuff usually. I'll get my screwdriver over here. Okay, what I've done, you could probably put any capacitor there, but these are very low impedance capacitors. These are that we used to use in two-way radio because they are really good. So the red wire here, that red wire goes there. I've just stuck this positive leg of the capacitor down there, and where this grey wire is the negative voltage, and sorry, that grey wire, not this grey wire, the grey wire here, that's negative voltage. So what I've done, positive goes to ground, so that's also connects to the positive wire there. I just put a bit of wire on, go around to the ground plane, so it's all nicely locked up. And your negative voltage comes off the board down here. Oh, that's what's out of frame. Couldn't see it. But you can see where the supply comes off. They've just taken it off one of the surface mount capacitors, right next to the clocking clunk 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 divider circuit. Well, okay, fair enough. I won't say anything about that, but as long as the noise doesn't get in there. So we've got that. Basically, the capacitor. See these two wires here. The capacitor goes on these two wires, but on the board. There you go. And all I did, I used Architect's copper foil tape, and I stuck it on because it's adhesive backed, and it's got a few little wrinkles in it. Doesn't make any difference, but yeah, and then just put it on and trimmed it with a knife. Make sure it's stuck really well. maybe even on the corners you could hot melt glue a couple of dabs to the top of the board, to the bottom of the board, just so um, in 25 years' time when the glue dries out, it doesn't fall off and fall into the circuit and blow it up. But I will be doing that anyway, and I will be tacking on the components so they don't fall off or vibrate off, and just stabilize the whole thing. So for this detector, it really is a relatively complex, a lot of stuff that's been done to it. I think, like I say, I think a lot of people have had multiple bites of the cherry at this, and yeah, even though the concept overall is sound, the application of the concept was a bit NQR, in my opinion. Right? I'll always say my opinion, just in case people don't like what I say, but it's just an opinion. You don't have to look at the electronic aspects of this as fact. I might have been, you know, talking out of my proverbial all the time, and that jitter makes no difference. Well, in my opinion, it makes a hell of a difference, but you may think it doesn't. I don't know. Just my opinion. Leave it there. So that is the VCO fix. Please put bypass capacitors on your circuit boards because that is critical for stability. Dear me. And also a good idea to put a ground plane on your circuit boards when you have things like oscillators and that. But if you're doing, I'll let you in a little secret, if you're doing anything front end work, don't put a ground plane around your input stage. Do you know why? Because it adds capacitance and slows down the transition of signals and reduces some loss. So there you go, guys. Another little secret for you. You have to structure things in a particular way. You still got to run a ground plane, but don't put it near your devices that are on the input part. Any protection devices or anything like that, don't have a ground plane under those devices, but around it and the power area and so forth, like that. And if you're using high impedance devices, if you want to go and use JFETs and you want to use impedance transformation, stuff like that, you should put in guard rings around the inputs of your JFET devices. But you probably already know all that, I hope. But some people don't, some people do. But yeah, it's a bit of a tricky art doing modifications to detectors because you just look at this and say, yes, the principle, yeah, nothing wrong with the principle. It's just how it's been applied, and all the finer points have been just omitted, which it's a bit like trying to eat a pie without a crust, without a casing around it, if you know what I mean. Make a mess. But yeah, that's that. That is a 2000. So now you get an idea why MindLab don't put VCOs in their detectors. They sort of do put a little bit of a VCO in there, but it's not a VCO. Well, it's yeah, it moves the frequency a little bit. That's how you got the fine tuning on your detectors in the back menus, or the automatic frequency scanning. But up until now, it's all been LC oscillators because they want to get rid of that phase noise. And yeah, it as an oscillator, LC oscillators are much cleaner than anything that is, well, basically anything is digital for a start, and anything is utilizing something else and clocking down, or from a digital perspective, it's a lot cleaner. But there you go. These are meant to be crystal controlled, so how good's that? Crystals are very, very accurate, don't move much at all, and are very clean on the output. But once that goes into that bunch of chopper dividers and all those chips there, and gets pretty nasty and messy. But that's just the design of these things. But frequency stability is probably the main aim, and that's why they were crystal controlled. The later ones, of course, they all changed, but they are all still LC oscillators. Anyway, that'll do. That's off. I'll turn my off. Now I have to get this off the bench, put it back together, and now I've got to go. Next detector I've got to do the bits are coming for that beach detector I've got from the UK. Thank God. I waited forever. And then I've got a 6000 to fix. That's going to be interesting. And after that, I'm going to get back into doing the front end for the 7000 design. And hopefully we knock that over. Anyway, that's how you fix these things up. Pretty straightforward. And you can probably see in the front end that little black blob. That is the 2SK1334 that I put into the circuit because it's less loading on the 4093. The chip there that's been replaced, the black one. See the black one? It's a 4093. So that drives the output. Sorry, not the output, but it drives the MOSFETs on the signal input, blocking the flyback voltage, blocking MOSFET and transmit blocking MOSFET. There is two of them in series. One's P, one's N, because these things negatively switch. Flyback is coming through on the opposite, on the positive. So you've got to block the positive flyback, and you've got to block the negative transmit waveforms, because the body diode inside the MOSFETs will conduct that negative transmit straight through into the op amp. You need to put another MOSFET there around the other way, so that diode, the body diode, blocks the 15 volts. So that's how it all works. And then the newer ones, they just use two ends and flick it around on the last one, and seems to work. Yeah. There's better ways of doing it, but we won't get it. You've probably seen some of the ways I've done it before, when I had complete floating front ends. People have tried to copy that, by the way. I'm trying to lay claim to it. Funny. But yeah, it's all out there. Go look at my early videos. You'll see what I'm doing, and then have a look at what people claim these days. It's all been done before over the years. But like I say, I don't want to go on too much about these things. This one too, you could have got really pedantic and put in, turn the power supply off, the oscillating power supply off during the receive cycle. But you need a lot of storage capability with your capacitors. And the thing is, what drives that rail is a 2N, I think it's a 2N 2000 or 2002, and it's not really made to switch big heavy currents. You'd have to modify the whole power supply, and even the inductor there as well. You can see it behind the blue capacitor. That's only rated for probably 100 milliamps or something, and you probably saturate it and then blow up the MOSFET. So there's a lot of tricks. You can't just go and bang things in everywhere and expect it to work. It's made. These are made to do exactly, supply the amount of current to what's there. So you just start adding stuff. It may load the voltage rails down. There's many ways of fixing that up, but then you got to start doing surgery on the board and stuff like that, and it gets time consuming and very complicated. So that's that. That's the fix. I'll call that the fix. So we'll see how Victor goes with it anyway. It seems quite punchy down low now. So working a lot better. Anyway, catches.